Hey y'all, we are going to, we're going to look at this one problem. Let me get to it. Okay, so what we're going to use is Descartes' rule of signs. This is actually my own little thing that I find annoying. I don't think that if something ends in an S, I can get my cursor there. I do the apostrophe, but you don't have to do another S. That was literally nothing. That was not math related at all, y'all. Okay, so we're going to look at Descartes' rule of signs. So what we have here first on that first bullet is the number of positive real zeros of a polynomial function f of x is either the same as the number of sign changes of f of x or less the number of sign changes of f of x by a positive even integer. If our function has only one variation in sign, then f has exactly one positive real zero. And it'll make more sense when we do an example. It always does. It'll make sense when you understand it. Just kidding. So the other bullet here says that the number of negative real zeros of a polynomial function f of x is either the same as the number of sign changes of f negative x or less than the number of sign changes of f negative x by a positive even integer. If f of negative x has only one variation in sign, then our f has exactly one negative real zero. So what we're going to do is we're actually going to list all the possible rational zeros or roots by using the rational root theorem. That's our p's over q's. Then after that, we're going to use synthetic division to test an actual root or zero. Before we do the synthetic division, we could actually plug in one of our possible roots into our function. If you solve that little equation and you end up getting zero, then great, it is a zero. We could go ahead and do synthetic division. Doing that could just keep you from trying and testing like multiple zeros or multiple possible zeros actually. Then from this information, we're going to use it to find the rest of the zeros. And that's really where the Descartes rule of signs comes into play, because if we have X amount of possible zeros, and even if we can find one zero, we need to be able to find the other zeros. There's a logical rule basically that states if our leading coefficient is cubed, we're going to have 3 solutions. If it's to the fourth power, then we're going to have 4 solutions. I think that might actually come up in the next section, but that will also be something that we kind of use to really be able to figure out the other zeros. I feel like the last 3 or 4 videos I've just been yawning. I've been doing nothing but recording videos, y'all. Okay, so I literally just typed in these problems. So as you can tell, didn't really have a way to actually make these squared and cubed. And I just did a little caret. So I already read what we're going to do. Now let's actually do it. Okay, so our problem is, it is implied that it's f of x, y'all. I know that on my A, I don't have f of x. It is set equal to 0. Let me zoom out here. Whether or not you do f of x and then that function, or you just write what it has written, it's the same thing. I'm going to have some continuity here, and I'm just going to write it the way that it's written. So list all possible rational zeros or roots, and what it is that I'm looking at is x cubed, a negative 5x squared, a positive 17x, negative 13, and then equals 0. My plus or minus p over q is a plus or minus. So my p is a 13. And then my q is 1. So y'all, this means that what we're going to have is plus or minus 1 and plus or minus 13. And that's technically just saying that if our q is the number 1, then our actual reduced possible rational zeros is going to be the positive and negative value of the factors of our 13. The only factors of 13 are 1 and 13, putting both of those over 1, taking into consideration the positive and the negative value of them, you just get positive negative 1, positive negative 13. So that tells us our possible rational zeros, are also known roots. What we're going to do now is actually look at the variation of signs so that it helps us with that last part where we find all the zeros. What we do to actually use Descartes, I'm actually going to use the fact that I already have it written right there. Like I said, this is my f of x, right? So what you do is, do you see how it said the number of positive real zeros of a polynomial function f of x is either the same as the number of sign changes? So our options is it's either the same as the number of sign changes or less the number of sign changes by a positive integer. You always use the positive integer too whenever you do this. And what it means by the number of sign changes is, let's actually look at our function. Do you notice how that leading coefficient is a positive 1? And do you see how it went from a positive 1 to a negative 5? That's one sign change. And then if you notice here, it goes from a negative 5 to a positive 0. I'm sorry, why did I say that? To a positive 17. That's our second sign change. And then we have positive to negative. I actually have 3 sign changes here. And the way I've always done this for my Descartes rule of signs, I'm looking to see what the positive real zeros are and what the negative real zeros are. And then, y'all, there's also imaginary zeros. There won't always be imaginary zeros, but there can be imaginary zeros. I looked at the sign changes of my function f of x, and I got 3. And then now what we're going to do is we're going to look to see what the sign changes are of our f of negative x. So we've done this before. Wherever you have an x, you're going to plug in negative x. We're going to use the exponent on our variable to see what the actual value is of our variable. So if you look here, I've got a negative x cubed. I know that if I have a negative variable raised to an odd power, what I get is a negative variable. And you keep your exponent. And then if I look at my negative x squared, I know that if I have a negative variable being raised to a positive power, I will always get a positive variable. So that would actually be a negative x, and then that changed to a positive x squared. And then, y'all, that's being raised to an odd power. And I know for a fact that negative variables raised to an odd power will always give me a negative variable. So I get a negative 17x, negative 13 equals 0. So now let's look at the sign changes here. If you look, I go from a negative to a negative to a negative to a negative. That was 0 changes. So looking at this right here and seeing that my function's highest degree, its highest exponent, the degree of the function is 3, that means I'm going to have 3 different factors that make up the factored form of this polynomial. And so if I have 3 positive real zeros and no negative zeros, that actually doesn't allow me to have any imaginary zeros because I can only have 3. The actual Descartes rule of signs says that we're either going to have the same number of sign changes or we're going to take away a positive integer from that value. Because I came up with 3 sign changes, we're either going to have 3 positive real zeros or we're going to have, if we take 2 away from it, we're going to have 1, correct? So I'm kind of just going to do this little table over here, and I'm going to consider all the different possibilities. I did just now look to see if I have 3 positive real rational zeros, I would have 0 negative and 0 imaginary. Let's pretend I had 0. Well, I already know for a fact I'm not going to have any negatives, but that would mean that I would have 3 imaginary zeros. So now let's look at the fact that Descartes' rule of signs says that I could also have the number of sign changes less an even integer. So I would get 1. Let's say I did have 1 positive real zero. I already know I didn't have any negative zeros. This would mean I would have 2 imaginary, right? And then what we could do is, I guess that would actually, that's my alarm. It's time to wake up, y'all. I guess that would actually be it right there. That's taking into consideration the 3 changes that I found, having none, and having an even integer less than the changes I found. I did the Descartes rule of signs here. I get 0, so each possibility is going to be 0. And then knowing that my exponent is 3, I'm going to have 3 factors. 3 and 0 make 3, 0 and 3 make 3, 1 and 2 make 3. Those are going to be my possibles as far as the actual zeros that I have for this problem. So now let's actually work on this problem. Okay, so what I'm going to do is I'm going to test one of these possible zeros. Like I said, you can actually plug it into your function, and then that way you can know whether or not it does work. I'm just going to go ahead and start with f of 1. I would get 1 cubed, a minus 5 times 1 squared, a positive 17, 1, negative 13. I know I just kind of keep doing the equal 0. I think it looks a little bit better if you don't, just for the sake of plugging something in. What I get here is 1 cubed is 1, 1 squared is 1, times negative 5 is negative 5, 1 times 17 is 17, minus 13. What I get here is I'm actually going to do 1 minus 5, which gives me a negative 4, plus 17 minus 13. Negative 4 plus 17 would be 13 minus 13. Do you see how I got a 0? So that tells me that 1 is a 0. Now, that is good as far as seeing if it's going to work as far as giving me a remainder of 0 in the synthetic division, but that actually doesn't give me the actual quotient as if I had divided by 0. So I do want to go ahead and divide by 0. And what I have here is the 1, negative 5, 17, and negative 13. Those are the coefficients for my original function. You bring down your first your first number, and then you do your multiplication. 1 times 1 is 1. And then we get right here, negative 5 and 1 gives me a negative 4. Doing this multiplication, I get a negative 4. And then what I notice here is I get 13. My 13 goes here. And yeah, if you do notice that you do have those same terms in the left-hand side when we plugged in f of 1, but there's no real way to easily state the ones that you keep and the ones that you discard and the ones that make up your new function. So let's go ahead and make sure that we use synthetic division here. What I would end up getting, because my original function started at x cubed, I'm actually going to have to rewrite this, but let me for now say I go down a degree, go down a degree. This is the quotient when I use synthetic division, using the original polynomial, dividing it by what I did find to be an actual 0. Now, it did let me do that. Perfecto. Okay, so this is the quotient that I got when I divided it. I did find out for a fact that 1 is a 0, which means x minus 1 is a factor. I'm going to take this quotient, and I'm also going to put it right here, right here. I need to find the other zeros, therefore I'm going to set it equal to 0. If y'all are okay, here we go. So I already know that x plus 1 is a 0. So I can say right here, x plus 1, y'all, that's from taking that factor x minus 1, setting it equal to 0, right? So now what I have is the other factor, which is x squared, a negative 4x, and a positive 13. If I look at that and I consider doing the AC method, what happens is I have my a times c, which is 13. That's prime. The only factors are 1 and 13. So in no way, shape, or form can those factors combine together to give me a negative 4, correct? So that lets me know what I actually need to do is the quadratic formula. My a here is 1. My b is a negative 4. I'm trying to see if I could do a different method. That would be negative 13. I could pull out my x. Yeah, let's just do the quadratic formula. It's just kind of like a surefire way to know it's going to work. The quadratic formula is a negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So I get 4 plus or minus 16. What is that, 52? It's a negative 52 all over 2. X equals 4 plus or minus 16 minus 52. Signs are different. Subtract, keep the sign of the larger. So already I see that I have the square root of a negative number, which means that I'm going to have my imaginary roots. And because I did Descartes' rule of signs, I have one real positive. That tells me I should be getting 2 imaginaries, which is what's going to happen doing the quadratic formula here like this. So what I get is x equals 4 plus or minus. You're going to take the square root of 36 and get 6. That imaginary unit comes out because of that negative under the square root. And then we have over 2. We could actually make this 2 plus or minus 3i. And so those would actually be our two roots right there. What we would do is in the homework or even in a problem, you actually just need to list the actual zeros that we found. So if you notice here, I get 3 zeros. My original function was x cubed, so that checks out. I did Descartes' rule of signs, and I learned that these were the different combinations that I could have had for my zeros, and I actually ended up having one positive real zero and 2 imaginary zeros. And so that would be how you will find all the possible zeros using Descartes' rule of signs. Sorry, my handwriting got super sloppy, but that is that. If you have any questions, y'all, make sure you ask, okay? Thanks. Bye.